Hello everyone, welcome back to MacTech 40, and today we will see the deflection of beam by conjugate beam method. Okay, first of all, let me tell you, if you are watching this video, then watch this video 360p or more than that. Why? Because today I'm not going to write anything because the writing tool is not working properly. So I have taken the images and underline what are the main points, and I will try to zoom out all this. Okay, so that you will easy to understand. Okay, so uh, first, what is conjugate beam? So conjugate beam is an imaginary beam with similar kind of loading condition. First of all, there are you know there are many deflection finding method. You can find the deflection by area moment method, Cauchy-Glennie theorem, strain energy method, the double integration method, all that thing. But whatever method you will use, result should not be changed. For example, simply supported beam with a point load at the center. So deflection is WL cube. If point load is W, then WL cube upon 48 EI. Okay. So if you find any of the method, then result should not be changed. Okay. So this is the method, which is conjugate beam method. What is conjugate beam? It is imaginary beam, or you can say that secondary beam. What we are doing, whatever our actual beam, we are drawing moment bending moment diagram, and then we are dividing with EI, flexural rigidity. Okay, then that M by EI diagram, whatever the graph you will get, if it may be triangular, it may be rectangle, or it may be a parabolic curve. So that curve, rectangle, triangle, or parabolic, it will become your load. For example, you know the uniformly varying load, it is a triangular shape, so it will become same. Okay, if your M by EI diagram is rectangle, then your loading for conjugate beam is that rectangular uniformly distributed load. Okay, if triangular, then it is uniformly varying load. So what we have to do in this method is, first we will draw shear force and bending moment diagram for the real beam, the beam that has been asked in the question. Then after bending moment diagram, we will divide with E by EI. We will divide with EI, and then whatever diagram we get, we will put another beam over there, and that beam will be our conjugate beam. Okay, or you can say that it is a mirror image of the real beam. Okay, and it is also known as method of elastic weight. Here all I have marked here. You can write this, like you can see this method of elastic weight. Also, why elastic weight? Because it is a flexure within the elastic limit, and it is divided with flexural rigidity of the beam also, whenever, because this beam is imaginary beam, not actual beam. So why this, from when this equation came? So before that, going to any derivation, we know that EI into Y, that is called deflection. Okay, if you take the derivative dy by dx, then it will become slope. If you take second derivative, then it will be negative of bending moment, we all know. Again, if you differentiate, then it will become derivation of bending moment. Here in equation 4 you can see that will become shear force, and again if you differentiate fourth time the deflection y, then it will become del f by del x. That means the rate of change of shear force at any particular point, it will give rate of loading w. We all know these relations, so we will use this relation in our method. Now one thing, write down somewhere, whatever the shear force diagram you will get as of conjugate beam, shear force diagram of conjugate beam will give you slope, and bending moment diagram of that conjugate beam will give the deflection for real beam. Okay, this is here all things I've written, and this is not I've written, but it's in book, and I am underlined that point also here. So this is basic about conjugate beam. What conjugate beam is? The imaginary mirror beam where the load is M by EI, whatever our actual bending moment divided by EI, that will be our loading condition. So one statement, the last statement that I will tell, that shear force diagram for conjugate beam, it is a slope, and the bending moment diagram for conjugate beam, it is a deflection. So this is a mathematical proof of it. If you want this PDF, then you can comment in this section. Okay, comment box, comment in the comment box that you will require PDF, then I will generate the link and I will send you a link. Okay, so this, because if I going to derive, then it will be very long video. So, and this is very easy derivation. Okay, so whatever I said, that is a mathematical proof. Okay, now second thing, the direct sign convention, direction, or you can say that sign convention. So for loading, if M by EI diagram is in below the line, like for example cantilever beam, your bending moment diagram is below your zero line, okay, or beam line. So you have to take elastic weight positive downward side. And if M by EI diagram, when sorry, loading of elastic weight, for example if there is a zero line, then your loading will be downward because it is positive direction. M by EI diagram, it is in positive direction here, it is written. And loading condition will be upward, that means down to up, down, okay, upwards when M by EI diagram is below the beam line. In case of cantilever beam, we know the triangular shape or parabolic shape, that is below the zero line, so it is, so in that case loading will be upward. Okay, next sign convention, that is slope and deflection, I already told you. Now let us take one example. This is the first example, the 14.1 as per the book, that determine the slopes at the ends and deflection at the midspan of the simply supported beam carrying a central point load W, and also plot the slopes and deflection diagram of the beam. That means our simply supported beam with point load W. So let me go on next page. This is the beam. Okay, this is the beam, simply supported beam with point load. So we know the maximum deflection occur at central, okay, center part, and maximum bending moment, that is also at center, and WL by 4, the magnitude is there. Now divide with EI, so M by EI diagram will be WL by 4 EI. Okay, and the shape is similar. Now this will become a loading condition. So here there are here the, as you can see, the conjugate beam with loading, C figure. So these are the reaction forces and this is the downward force. So all the calculation are done here. WL cube upon 16 EI, WL square upon 16 EI. You know very well the equilibrium condition. The taking moment about one of the point is 0. So you will find RA and RB, sorry, RA dash and RB dash, that means reaction. WL square upon 16 EI. Okay. Then bending moment diagram. Sorry, first of all shear force diagram let us draw. So here there is a point load, so there is a sudden rise and then gradually decrease because area is increasing. So here shear force is 0 0, and this is like this, the positive and negative. Okay, so here maximum value is WL square upon 16 EI, that is the maximum shear force value for conjugate beam. So that maximum shear force value, that means maximum slope, and the maximum slope in case of simply supported beam we know that is at the end, at the loading and A and B dash, A and B point. Okay, so WL square upon 16 EI, that is the maximum shear force. And what maximum shear force of conjugate beam? It shows deflection of the real beam. So this is the deflection, WL square upon 16 EI. Okay, now if you draw this bending moment diagram, so it is with cubic curve, WL cube upon 48 EI, because first this is the calculation. They have taken the moment at the about C. So there is RA force into L by 2 distance, positive slope, and then this is the triangular area, uniformly varying load. So its weight will act as a CG, that is from 2/3 from the point A. Okay, so what, after the calculation you will get WLK upon 48 A, that is the maximum bending moment value, and the curve follows, that is cubic curve, and the maximum bending moment value will give the maximum deflection, and in simply supported beam maximum deflection at the center. Okay, so this deflection value, this will give you the deflection at W L cube upon 48 Ti. So this is the method. Okay, next we will take an example of cantilevers, but there is one change in cantilever. What the change is, in cantilever whatever fixed end will become free end and free end will become fixed end. Okay, here as you can see here in figure C, and a bending moment diagram is downward. Okay, so loading will be upward side as you can see in the figure here. Okay, and we will solve the same method. If you want the PDF, then again I'm telling you, ask in the comment section. I will provide the link, the whole chapter with some practice problems also, and not too much complicated cases will be asked in a gate exam or maybe in engineering service prelim. Okay, so this is the thing. Now in simply supported beam, we do not have to change anything, but in cantilever and roller support, sorry, internal roller, we have to change some condition. Okay, so what are that condition, please keep in the mind. Sorry, yes, this is some sign convention. If this is the real beam and conjugate beam, if there is a hinge end, that means simply supported case. So in conjugate beam there is also a hinged end, or you can say that no change. If there is a free end in real beam, then it will become fixed end, and fixed end become free end. If there is a roller support, then it will become roller support, but there is an internal hinge. Okay, like the internal welded joint, that is some points here you have solved the numerical, that all the deflection point, all the maximum stress will occur at C. We have solved the question in previous question, that is one question also asked in the gate exam. So the internal hinge will become roller support or interior pin, that means internal pin joint. Yeah, but it will depend upon condition. If both ends are fixed, suppose this is internal hinge and here left side there is a fixed joint and here is a fixed end, both the beam with both side fixed, then your internal part will be become interior beam, this internal hinge will become interior beam. And if here both hands there is a simply support, then it will become roller support. Okay, and vice versa the same. And here the same, this kind of, if there is a link and they are connected by two roller, one roller is connected to with link, so then it will become simply one roller. Okay, and constant length beam, and vice versa. So these are some sign convention. Okay, that you have to remember it. Again I'm telling you, if you want this PDF, then come ask in comment section. I will tell you the PDF, where that I will tell you the link where the PDF is, and in that PDF there are some practice question also. Okay, so this is hope, I hope you understand this. And this is a very short video, and there are some those uh, those people who do not understand that, please go back and watch again, because there is not a writing tool is not available with me, and there is damaged now and it is not working properly. I'm writing there and it is not writing something on the screen, so I've decided to go like this. Okay, so thank you for watching this video, hope you enjoyed it. If you have any doubt, just ask in the comment section, and we will meet in next video. Thank you.